Hi everyone, I'm Dr. Surjit Singh. In this video on Python via examples, we shall talk about the Monte Carlo experiments. It finds its use in artificial intelligence. Let us begin. In this session, we will learn about Monte Carlo experiments and their applications. We'll take up a few simple experiments using Monte Carlo technique. They are useful in many areas of artificial intelligence. Monte Carlo experiments are computational algorithms which rely on repeated random sampling to obtain numerical results. The name Monte Carlo comes from a place in Monaco where this technique was initially developed. Our previous video on Monte Hall problem is an example of Monte Carlo experiments. In this problem, we used random numbers to arrive at its solution, in which we discussed the distribution of probabilities amongst the three doors. Scope of Monte Carlo experiments is much wider. It is helpful in those problems where analytical solution is impossible or is very tedious. It finds utility in vast areas like share trading, weather forecasting, nuclear reactors, and many more, where early and fast knowledge is essential to prevent disasters. Steps followed in Monte Carlo experiments are to define the problem, set up random inputs, run simulations, collect results, and analyze them. In this session, let us learn about some more Monte Carlo experiments. Evaluation of pi is an enduring challenge in number theory on which a lot of work is still done. Being an irrational number, pi cannot be expressed as a simple fraction, and its analytical computation relies on the summation of infinite series, which has very slow convergence. It takes 100 terms to compute pi correct up to 2 decimals. For details, you may refer to the 11th video of this series. As an alternative, let us find the value of pi by a Monte Carlo experiment. Area of a circle is pi r squared. If the radius of the circle is 1 unit, its area is the numerical value of pi, which means that the segment of the circle within the square gives pi by 4. Let us proceed to find the area of this segment of the circle. Monte Carlo approach of this is very simple. We place a large number of points randomly everywhere within the square. Density of the points is uniform, and total number of points refer to the area of the square, that is 1. Fraction of the points that lie within the segment refer to the number pi by 4. Let us now write the Python program to carry out this Monte Carlo experiment. We take 100,000 random points and initialize a counter to 0. We now start a loop over the number of points. In every iteration of the loop, we create a new random point within the square. This form of a random function call returns a random number between 0 and 1. We call it twice to get random values for both x and y coordinates of the point. If x squared plus y squared is less than or equal to 1, the point is inside the segment and we increase the counter by 1. If the random point is outside the segment, we leave the counter unchanged. One by one, for loop runs for 100,000 random points. In a typical run of the program, number of points found inside the segment are 78,583 out of a total of 100,000 points. Area of the square is 1, so this ratio gives the area of the segment of the circle, which is the value of pi by 4. It also gives us the probability of a point being found inside the segment. We multiply it by 4 to get the value of pi, which is correct up to 2 decimal places. Results are similar in every run of the program. Next example is of finding the integral of a function. Consider the function x squared. Integral of x squared between the limits 2 and 5 is a very simple problem in calculus, and its analytical solution is readily available. Integral of x squared is x cubed by 3 between the limits 2 and 5, for which the result is 39. We now learn to find the same integral by Monte Carlo experiment. Integral of a mathematical function is the area under its curve. Let us make a plot of x squared against x. X range is 2 to 5, and we select the function range between 0 and 30. At x is equal to 2, the function is 4, and at x is equal to 5, it is 25. The curve of the function x squared divides the rectangle into two parts. By definition of the integral, area below the curve is 39, that is the value of the integral. Total area of the rectangle is 90 because its x range is 3 and y range is 30. So the area below the curve is 43.33% of the total area of the rectangle, and the problem reduces to finding the fraction of the area below the curve. We can readily visualize that the Python program will be on the same lines as the previous program. We define x squared as the function. The limits of x are 2 and 5, so the range of x is 3 and that of y is 30. The range of y ensures that the entire curve is within the rectangle. We take 100,000 random points within the rectangle. In the beginning, count of the points below the curve is 0. We start a loop over the points. A random function gives a number between 0 and 1. We multiply it by 3 and add 2 to it. The result is a random number between 2 and 5. Suppose that it turns out to be 2.91. We save it in x. Another random number multiplied by 30 gives a random value to y between 0 and 30. Suppose that this random value turns out to be 6.45. The pair becomes a random point in the rectangle. We now want to find if this point is below the curve or not. So we find the function value at the x value of the random point, which is square of 2.91, that is 8.48. It is clear that y value of the random point, that is 6.45, is less than 8.48, the function value at the same value of x. So the random point is below the curve of the function, and we increase count by 1. Again, suppose that in the next iteration of the loop, the y value of the new random point turns out to be more than the square of its x value, so we ignore it. This means that out of these two random points, one is below the curve while the other is above it. The loop will continue. Every time a point comes below the curve, we increase the count by 1 and ignore it if it is above the curve. This loop runs 100,000 times, processing one random point in each iteration. At the end of the loop, we have the count of the points that are below the curve. Fraction of the points below the curve is the count divided by the total number of points. If we multiply it with the total area of the rectangle, we get the area below the curve, which is the required integral, and we print it. The result of the integral in every run is close to 39. This means that we are successful in carrying out Monte Carlo experiment for finding the integral of x squared. We may think that there is hardly any use going for Monte Carlo experiment for finding the integral of x squared, but we can easily adapt this method for complicated functions. Let us find the integral of this function between the limits 2 and 5. We all know that it is very difficult to find this integral, if at all it is possible. But we can readily transform the previous program for this function. we revise the definition of the function and import the log and sine functions in the program. If we now run this program, we get the integral as 74.4, but wait, we have not set the range values of the function. For this, let us run a supplementary program in which we print the values of the function at different x values in a loop. Output of this program gives us the function values at various values of x between the range 2 and 5. Some of the values of the function are more than 30, so the plot of the function goes outside the rectangle. This means that we have not correctly evaluated the area under the curve. So we increase the y range from 30 to 40 and enlarge the rectangle. Now that the function is entirely within the rectangle, we proceed with our Monte Carlo experiment program with new y range. Its execution now gives the correct value of the integral. This illustrates that it is very important to ensure that the curve does not go out of the rectangle, otherwise the results are seriously in error. There is no further change in results if we increase the y range further to 50 or to 60. Both the curves that we have discussed are smooth, but there can be curves in which there are sudden and erratic fluctuations like in the noise waves. In such cases, Monte Carlo method is the most suitable. Problem reduces to setting up of the function after finding the parameters on which it depends. In this session, we introduced a couple of Monte Carlo experiments. The first problem was about finding the value of pi, and we wrote the Python program about that. Next, we talked about the numerical integration and applied it to find the definite integral of a complicated function for which analytical solution is not possible. I hope you enjoyed the video. Please feel free to ask for further clarifications on my email address given below. I'm looking forward to your comments. Please stay tuned for more such videos.